Well, hello, Whiteboard Economist here, and welcome back to my channel. This is the next video for my series in Calculus 1. And if you look on the board, you see the topic for today is Introduction to Derivatives. Well, what is a derivative? Some of you may have heard this term before, some of you may have not. But a derivative is just a fancy way of saying rate of change. Now, why is this so? Well, let's illustrate this principle. Let's say you have a person here, just standing here, just chilling, and then you have a car driving away from the person at 50 kilometers an hour. Now, what's the rate of change of the car's position relative to the person? It's 50 kilometers an hour. But let's graph this. So let's put distance on this axis, we'll put time on this axis, and so after an hour the car is 50 kilometers away from the person. After 2 hours it's 100 kilometers away from the person, and after 3 hours of course it's 150 kilometers away from the person. Now if you just graph this, you get a curve. Well, you don't get a curve, you get a line, and the slope of the line is 50. Alright, so the rate of change of the car's position relative to the person is 50 kilometers an hour, because after every hour it's 50 kilometers further away from the person. And so from this you know that the velocity is equal to rate of change, and since the slope is 50, we've also established that the slope of a linear function is equal to the rate of change. Alright, so now you're probably saying, well, this is not something I don't know, so why are we making such a big deal out of this? Well, because this is not a derivative yet. This is just a brief introduction to the introduction to derivatives, but this principle is very important, so I just wanted to make sure that you know it. Because what if I give you a more complicated example? You know, what if instead of a linear function you have this? But again, just remember, slope of a linear function is the rate of change. But let's say I give you a cliff, alright? So, and for whatever reason, you have this guy standing on top of a cliff. And let's say if he jumps off, let's not make him jump off. Let's say he throws a rock off the cliff. Alright, and because of gravity, the rock is going down where it's towards Earth at 9.8 meters per second squared. If you taken physics, you know why. If you haven't taken physics, just believe me. What this is saying is the rocket is accelerating at 9.8 meters per second squared, meaning after every second it's going 9.8 meters faster than it already was going. So let's graph the speed of the rock. Let's put velocity on this axis, we'll put time on this axis. Since we established that velocity is rate of change, the velocity of the rock goes like this. It's increasing at an increasing rate since we have a square right here, and you'll notice right off the bat that this is not a straight line. This is a curve, and if you have a curve, it's not as easy to find a slope of a curve. So what if I asked you to find, the velocity at this point in time, find the rate of change at this point? Well, how would you do it? You can't find the slope right here because it's a curve, so you'll have to use something called the tangent line. What is the tangent line? Well, the tangent line is a line that touches the curve at only one point. So this is your tangent line. And the slope of the tangent line, whatever it is, will be equal to the rate of change at this point in time. And this is where derivatives play in. But first, you're probably asking, well, why is this true? Why is the slope of the tangent line equal to the rate of change at that point? Okay, well, let's illustrate this. Let's move this curve to this side. Let's say move it to here. This is your original curve. Your point right here. Alright, so let me erase this part first. So why is the tangent line at that point the rate of change? Well, if you look at it this way, if you take this curve and take this little section of the curve and just blow it up, alright? So, if you blow it up, it'll look something like this. It's still a bit curvy, but flatter than this part of the curve. And this is your original point. So, now you take this section again, blow it up again. You know, just zoom in again. Alright, so now your curve starts looking like this. It gets flatter and flatter. And again, you zoom in. Eventually, you'll reach a point where it will look just like a straight line. And this straight line, the slope of this straight line will be the same as your slope for the tangent line. So this is why the slope of the tangent line is the rate of change, because it's equal to the slope of the curve at this point, once you get in close enough. Alright, so now how would you find the slope of the tangent line? Okay, so before I do anything, let's go over the slope of a line in general. How would you find a slope? Well, m is equal to delta y, or change in y, over delta x. For our intents and purposes, it's delta f of x over change in x, or delta x. So how does this play in? Well, let's say let's just have another example. Let's say I give you a curve that looks like this. Alright, so let's say I wanted you to find the slope of the tangent line at this point. Right? And for sake of demonstration, we'll call this point A. So, and this of course is A and then f of A. So you'll notice that you only have one point. Well, how do you find the change by just using one point? You can't. So what would you do? So to do this, I would just pick another point arbitrarily on the curve. Let's pick this point. Alright? So now let's call this point x. And of course, this part is x and then f of x. So now you have 2 points. And clearly, if you draw a dotted line from here to here, that's the distance between x and a. So x minus a is equal to the distance between these 2 points. And this right here, f of x minus f of a, that's the distance between these 2 points. Now you're asking, well, why did I do all this? You know, why did I just randomly pick a point and then draw these random lines and subtract random things? Well, if you draw a line between here, this is called a secant line. You draw the secant line connecting these 2 points. What do you get? Well, now you have a line. Can you find the slope with this line? Yes. Change in f of x minus f of a, that's delta f of x, over delta x. Well, this is your delta x, the change in x, rise over run. So that's x minus a. So now we found the slope with this line, but you're asking, well, these 2 slopes are obviously different. So how does finding the slope of this line help with the tangent line? Well, remember, I just picked this point arbitrarily. It doesn't have to be here. In fact, we're going to move it closer. We're going to shift x towards a. Let's say we move it here. Alright, so your new line is here. And of course, you can find this slope pretty easily. Just go through the same process as you did for here. Alright? And so, just to move things on, let's move it even closer to point A. Let's say our x is actually right here, and the slope of the line is here. Now you'll notice, as we move closer and closer to A, the slope of these lines get closer and closer to the tangent line. In fact, that's the whole point of this. The point is to move point x closer and closer and closer to A, and eventually the slope of the tangent line will approach this. Well, the slope of the secant line will approach the slope of the tangent line. Alright? So that's how you find the slope of the tangent line, but we're going to need to make a slight adjustment to this formula, because originally you only had 1 point, and you can't take rates of change for just 1 point. So what would you do? Well, we've already established that this holds true, f of x minus f of a over x plus x minus a. So obviously this will be part of your equation. F of x minus f of a over x minus a. But how will we illustrate, moving x closer and closer to a? How will we show this on the equation? Well, you'll notice that as we move x closer to a, that's pretty self-explanatory. X is getting closer to a. So immediately you should think, well, that just means limit function. The limit of x approaches a, because that's literally what we're doing, x approaching a. So this will be your equation for the slope of a tangent line. Now, more than likely you'll see this written in a different form occasionally. Instead of f of x minus f of a over x minus a, it's sometimes written as f of a plus h minus f of a over h, and of course this becomes h approaches 0. Now, why is this true? Why is this equation, so here's your original equation. As x approaches a, f of x minus f of a over x minus a, right? So how are these two equations equivalent? Well, if you recall from our earlier videos, we've established that once you have function notation, it doesn't matter what goes inside of parentheses, as long as it stays consistent with some other part of the equation. Well, how do you make these two consistent? It's just a matter of relabeling the points. Instead of here we have it labeled as x, but let's label it as a plus h, because it doesn't matter what we labeled it, that was arbitrary. So if we label it as a plus h, obviously this becomes a plus h f of a plus h. So right off the bat, we've reconciled this difference. F of x becomes f of a plus h. Now let's take care of the denominator. This used to be x minus a, so x minus a, but now since x becomes a plus h, this becomes a plus h minus a. Well, a's cancel out, so this leaves you h. So this accounts for the denominator. Now the final part is accounting for the limit. It was x approaches a, now it's h approaching 0. But remember from the last equation, when this was x, as x approaches a, this used to be x minus a. But as x approaches a, we're saying x equals a. So if x equals a, this equals 0. And so this is saying x minus a approaching 0. So now instead of x minus a, we have h. So it's x minus a approaches 0, h approaches 0, since we changed it. And that's why instead of x approaching a, we have h approaching 0. And this is why these two equations are equivalent to each other. And this is also an equation you can use to find the slope of a tangent line. Now, I've given you the equations. Of course, this seems a bit complicated at first. It is, if you haven't seen this material before. So naturally, you're going to need to do some practice. So in the next video, we'll go through some practice problems. We'll do some tangent line equations. We'll find some slopes. Of course, there are problems in your book as well. So go ahead and do those. But that's all the time what you have for today, and I just wanted to give you the equations and a brief introduction to derivatives. So we'll definitely do some more practice problems so you'll get a better idea on how to use these lovely formulas. But I hope you enjoyed watching this video and found it informative, and as usual, have a nice day.